Let's now talk about two other intermediate operations that are very common, filter and flatMap. And we'll compare and contrast both of them to map. Filter and flatMap, like map, are both stateless run-to-completion operations. And we're also going to talk about a very curious limitation with flatMap that makes it ineffective for parallel streams. And this turns out to be very important because for your programming assignment 3B, you're going to have to work around this limitation by using the idioms we're about to describe. So let's talk about filter first. So what filter does is it tests a predicate against each element of an input stream and returns an output stream that contains only the elements that match that particular predicate. Therefore, the number of elements in the output stream might be less than the number of elements in the input stream, which depends, of course, thoroughly on whether or not they match the predicate. If everything matches the predicate, then you're fine. It's the same number. If something is less than the predicate, that will be dropped. Here's how we apply this in the context of our simple search stream program. You can see that we take the list of search words, we find the list of words that match, which creates a stream of search results, and then we filter out empty search results, leaving only non-empty search results that are going to be processed henceforth in that particular stream pipeline. Note, by the way, that unlike map, which can change the type, change the value of the elements, filter cannot change the type or the value. It just can decide not to let it go, or it's purely a filtering operation, not a transforming operation. Here's how it gets applied in the context of the actual code. You can see we say filter, and we negate the results of search results is empty, which is a method that returns true or false. Once again, marvel at the wonderful fluent interface style that chains everything together in a clean pipeline-like way. Now let's talk about the flatMap operation. This is a more interesting operation in many ways than what we've talked about so far. So what it does is it returns a stream that replaces each stream element with the contents of a map stream provided by applying the provided mapping function to each element. Now, at first glance, it's like, gosh, that sounds pretty much exactly like map. How does it differ? Well, you'll see it differs in a very important way. Number one, most important thing, is the number of elements in the output stream can differ from the number of elements in the input stream. Whereas map, they always need to be one-to-one, same number of input elements, same number of output elements. For flatMap, you could have the same number, you could have more, or you could have less. So it'll give you the full range of options, depending, of course, on what it is you're doing. So here's a simple example where we're going to have a stream of lists of strings. So we take an array of lists of strings, we turn it into a stream of lists of strings using the of method, and then we apply flatMap, passing in the list stream behavior, and what that does is it flattens the list of strings into a stream of strings. So I always like to visualize this as a steamroller, right? It steamrolls over and flattens those things. So it'll go ahead and flatten everything out, so you'll then end up with a stream of strings, which can be very useful. So in this particular case, let's say for sake of argument, we had 4 input lists, each of which had 10 items or whatever. Then when it's all done, we'll end up with 40 elements in the stream. So now we have more elements in the output stream than we did in the input stream because we've taken the input and flattened it because it was basically aggregate or composite structures that are now flattened. This is a very, very useful, very, very powerful operation. FlatMap also may change the type of elements. It doesn't in this particular case. We have a stream. Well, I guess it does. We had a list of strings, and now we have a stream of strings. There's still strings involved, but before we had a list, and now we have just a stream of strings. This is how you could do this. You could have a bunch of lists of strings, which don't have to have the same number of elements in each one. We make ourselves a stream of them, and then we flatMap it using list stream, and then we can do some other stuff to it. And I actually have an example that shows how to do this in the EX12 project in my Java 8 folder in my live lessons GitHub repository. FlatMap is super cool, but it has a limitation that will bite you if you don't understand the limitation. And it bit me a number of times till I finally figured it out. So the limitation with FlatMap is it forces sequential processing. Even if you say, I want you to run as a parallel stream. And you can read this Stack Overflow article that will explain sort of how it works, and it points to this implementation code. This is actually the source code for the implementation of flatMap in Java Streams. And you can see what it does is it forces everything to be sequential, which is kind of weird. I'm not entirely sure why they did it this way. I know that they did it this way. I know it has to be something you take into account. I'm not sure quite what the motivation was. But at any rate, it's a pain and will bite you if you are not prepared for it. I have a really cool example here in my EX35 project in Java 8 folder in Live Lessons GitHub repository that demonstrates this limitation with flatMap. And it's really cool because you can actually literally see it. You can visualize it. It'll show you the threads that the code is running in. And if you use this in parallel, it still runs sequentially. Even though we said, I want you to run in parallel, please. It'll do things sequentially. So how do you solve this problem? How do you solve a problem like the flatMap? To riff off of one of the famous songs from The Sound of Music. So what you can do here is the following idiom. Rather than having .flatMap and then suffering with the slings and arrows of outrageous sequential processing, instead you use map. And map does not have this limitation. Map is going to happily run things in parallel. But the problem with map is it doesn't flatten stuff. So what we do is we then add to map the following two methods after the map. .reduce Stream.concat orElse Stream.empty. And what this is doing is this is taking all the stuff that's running in parallel and reducing it and concatenating it together. So concatenating is basically what flatMap is doing, except for the fact that this will actually run in parallel. And you can, again, prove this to yourself by running the EX35 example here, and it'll show you how this works, and it'll demonstrate it runs in parallel. And we need to have the orElse Stream.empty because if it turned out that there was nothing in this stream, we'd want to be able to return an empty stream. This orElse Stream.empty is just kind of syntactic sugar, much like what you had to do when you used find first in your first two programming assignments to get the first item, which returns as an optional. So interesting, interesting, interesting. You will get a chance to use this particular idiom over and over again in assignment 3B, where you have to systematically replace the use of flatMap, which is in assignment 3A, in order to be able to get the right behavior for parallel processing. And you'll also be able to see this when you run your program, because if you do it wrong, then your parallel streams program will only use one thread. And you can see that when you run this in the emulator. But if you do it right, it should use more than one thread, probably 3 or 4 threads. So that's the end of the discussion of stream operations, filter, and flatMap. Definitely a bit more interesting than map, and you need to be aware of the limitations with flatMap in order to use parallel streams properly.